Hi everybody, let's look at this one right here from 2008. We got a fountain shooting up here. So let's look here. It says we got a fountain with an opening of radius 0.015 meters. It shoots a stream of water vertically into the air at ground level at a velocity of 6 meters per second here. And then don't forget that the density of water is 1,000 cubic meters per kilogram here. All right. So first off, they say calculate the volume flow rate of the water here. So I'll use that funky V to stand for volume flow rate. And remember that that is area times velocity here. So our area, we're going to have to calculate here because they give us the radius. So that's going to be pi r squared times the velocity. And just so you know, these are velocities here, not volumes or volume flow rates. And so now we just need to plug in and solve for this. So we've got pi, the radius they gave us is 0.015 meters. Don't forget to square that. And the velocity is 6 meters per second. And so if you calculate all of that out, you should get 4.2 times 10 to the negative third cubic meters per second of volume flow rate. All right, next part here is we are going to find, it says the fountain is fed by a pipe that at one point has a radius of 0.025 meters and is 2.5 meters below the ground here. So let's draw that up here so we can sort of imagine that. So the pipe is continuing down beneath the ground, and at some point here, the pipe extends out and gets wider right there. And so at a point, let's just say right here, we'll call this point 2. This right here is 2.5 meters below the ground. So we'll call this point right here point 1, let's say. And then can you see that? Point 1 is right here at the ground level, and then point 2 is beneath the ground level. And so we want to find the absolute pressure of the pipe at this point. So since we have pressures and water flowing in different sized pipes at different heights, that lets us know we're going to use Bernoulli's equation. So let's write out this monster. Pressure at point 1 plus the density times gravity times the height at point 1. Let me switch pens here. This red one's dying on me. Plus 1/2 times density times the velocity at point 1 squared is equal to the pressure at point 2 plus the density times gravity times the height at point 2 plus 1/2 times density times the velocity at point 2 squared. All of that. Now a few other points here. Let's call this point the ground here at point 2. So if we do that, then this height right here drops to 0 and that part will be gone. And then the other thing is out here at point 1, we are at atmospheric pressure because we're open to the air there. So the pressure here is going to be atmospheric. So let's rearrange this. We're trying to solve for the absolute pressure down here. So the pressure at point 2, which we're trying to solve for, is going to be equal to, I just need to subtract this term to the other side. So we have P1, which I'm going to replace with P atmospheric, plus density times gravity times height 1, plus 1/2 times density times velocity 1, and I'll put my little arrows there, squared, minus 1/2 times density times velocity at 2 squared. And now I'm ready to start plugging in, but here we're going to run into a little bit of a problem. I know atmospheric pressure. I know height 1, it's 2.5. I know velocity 1 here. It shoots up at 6 meters per second. But what's velocity 2? We get stuck there. We're going to have to go on a side mission here to find that. We're going to use the continuity equation to tell us that because they told us that there was a change in the radius. That means a change in the area. That means a change in the velocity. So let's use the continuity equation. We know that the area at 1 times the velocity at 1 is equal to the area at 2 times the velocity at 2 there. Okay, so now area at 1 is pi r1 squared, and we'll multiply that by velocity 1, and area at 2 is pi r2 squared times velocity 2. We can get rid of these pi's, by the way, they're on each side. And so now we can plug in and solve. The radius at point 1, that was up there. They told us that earlier. That was 0.015 meters, but we can't forget to square it. And we know that the velocity up here at this point is 6 meters per second. We know that the radius down at this pipe got bigger, which, by the way, before I even start to do some plugging in my calculator, I know if the radius and therefore the area gets bigger here, that this velocity that I'm going to wind up solving for has got to drop. And if you calculate all of this out, 0.15 squared times 6 divided by 0.25, you will get a drop down to 2.16 meters per second. And that is at least a plausible answer, right? Excuse me. It's got to get less there. So now, let's start to plug in all of these numbers now that we know that second velocity there. So the pressure at point 2 is going to be 100,000. And I know I'm a bad physics teacher here, but I can't be bothering to write in all these units with all these numbers. The density of water is 1,000. Gravity is 10. The height at point 1 is 2.5 meters. And then add in this term, 1/2 times the density of water, 1,000, times the velocity at 1, the opening, be careful, that's the 6 meters per second squared, minus 1/2 times the density, 1,000, times the velocity at point 2, which was the 2.16 meters per second. Don't forget to square it. Do all of that algebra, and you will get that the pressure at point 2 is roughly 140,000 pascals, depending upon where you round off there. All right, now it says, the fountain owner wants to launch the water 4 meters into the air with the same volume flow rate. And so we're not going to change that. So a nozzle can be attached to change the size of the opening. Calculate the radius needed on this new nozzle. So we want to change the area so we can change the velocity in order to shoot it 4 meters in the air. So first thing we need to do is come up with some way to figure out how fast do we need to be going to get 4 meters in the air. And the easiest way to do that is with conservation of energy. So the kinetic energy will become gravitational potential energy at the peak. And so that is 1/2 mass times velocity squared is equal to mass times gravity times height. The masses cancel out on each side, and when we solve for velocity, you should basically have this equation memorized. We get 2 times gravity times height. And if we plug in for our numbers here, we get 2 times 10 times 4, and you will get a velocity basically equal to 8.9 meters per second. You can also solve this with kinematics, by the way. You can use what we call the fifth equation here, and you can use this and solve and still get 8.9 meters per second the same way. All right, so now we know that our velocity is. Now we can figure out what our area's got to be in order to get that velocity using the continuity equation. So area 1 times velocity 1 has got to equal area 2 times velocity 2. Once we figure out those areas, we can figure out the radii. In fact, actually, let's just plug that in now. So the area of 1 will be pi r1 squared times velocity 1, and that will equal the area of 2, which is pi r2 squared times velocity 2 here. Once again, we can cancel out those pi's. They're on each side. We don't need them. And now, what are we calling 1 and 2 here? Well, you really have some leeway here. I'm going to go back to thinking about this is point 1 right here when we left the fountain, and then this is going to be, sorry, not up there, the little nozzle that we attached on here. So that's going to be point 2 there. So I'm going to use this point here when we had this radius and this velocity right there. I'm going to call that point 1, and then this new velocity here is going to be point 2. So if I want to rearrange this and solve for velocity 2, I get radius 1 squared times velocity 1 divided by radius 2 squared. And let's plug in there. Radius 1 was 0.015 meters. Don't forget to square it. Velocity at that radius was 6 meters per second. And then I'm going to divide this down here by, sorry, this shouldn't be radius 2. I messed this up here. This should be, I'm solving for velocity, I'm solving for radius, excuse me, not velocity. So this should be radius 2, and this down here should be velocity 2. And also, since that's squared, that means I've got to take the square root of all of this. Sorry, made a little mistake there. And so now, fixing that, velocity 2 is what we solve for over here, which is 8.9 meters per second. And I've got to take the square root of all of that. So 6 times 0.015 squared divided by 8.9, and that should give you roughly 0.012 meters here as your radius at point 2.